Hi, and welcome to my talk. This will be on the results in computable model theory of continuous logic. This is some of my past research that I've been doing in preparation for my dissertation at Iowa State University. I'd like to thank the Association for Symbolic Logic for allowing me to give this talk and allowing me to still upload it, even in the current circumstances. But once again, I'd like to thank you for watching this video, and I hope that you are intrigued, at least, by some of my research. So let's get into it. Here's a plan for the presentation. I'll first go over some preliminaries on continuous logic. Then we'll talk about how I'm effectivizing continuous logic. And then I will discuss my first main result, which is a version of the effective completeness theorem. And then I will discuss a second result, which is in computational versus syntactic complexity. All right, so some preliminaries on continuous logic. Most of us are familiar with first-order logic. The language of first-order logic contains variable symbols, connective symbols, quantifier symbols for all exists, and a binary relation symbol equals. And so well-formed formulas in first-order logic look something like this. In this case, P's, Q's, and R's are unary predicates. But this is what we're familiar with. So these work great in the discrete case. But representing continuous structures in this setting can be tedious and sometimes impossible. So let's see how this translates over to continuous logic. The language of continuous first-order logic contains variable symbols, just like before. But now our connectives are going to take the shape of symbols representing continuous functions from 0, 1 to the n back into 0, 1. Right? So we have a symbol for every single function in this set. And our quantifiers are going to be sup and inf. And then we're going to have a binary predicate symbol, which is actually our metric, d. So now well-formed formulas of continuous first-order logic look something like infimum over x1, x2, d of x1, x2, or supremum over x0 of 1 minus d of x0 to 0. And this will actually be interpreted as and. So this is and 1 minus the metric between x0 and 0. You'll see why that's interpreted as and in a bit. But basically, this second one, this one on the bottom, this can be interpreted as the principle of non-contradiction. Now, the truth values in continuous logic is the closed set 0, 1. 0 is going to indicate truth, and 1 is going to indicate falsehood. I know that looks weird right now, but you'll see why we want that in a bit. Defining x as the just the set containing 0 and 1, and d as the discrete metric, continuous logic actually collapses into classical first-order logic. In this sense, it can be thought of as a generalization. Now, unlike classical logic, since 0 represents truth and 1 represents falsehood, the V operator, interpreted as a maximum operator, actually acts as an AND gate, and the wedge operator, interpreted as the minimum operator, actually acts as an OR gate. Okay, so now we're going to let M and D be a complete bounded metric space. When we say predicate, we mean a uniformly continuous function from M to the N into 0, 1, into our space of truth values, which somehow describes the objects of the space, right? So it assigns a truth value to them. The metric can be thought of as a binary predicate since it describes how far away two objects in M are. That is, if they equal 0, it's true that they're equal to each other. Now, a function, when we refer to a function, we mean a uniformly continuous function from M to the N back into M. Right? So it takes n many points of M and it outputs some other point in M. For example, x squared, that's a function from 0, 1 to 0, 1. It's a function in the classical sense, but it's also a function in our sense, if 0, 1 is our metric space. All right, now a metric structure is a tuple. It looks like this. It has our metric space as before with a metric. And then it has a bunch of R's, which are predicates, a bunch of F's, which are functions, and a bunch of A's, which are just some designated points. Now, an example that you can think of with this is just the closed interval 0, 1 with the Euclidean metric, bounded rational polynomials, and then our rational points are going to be the designated points. Okay, a signature over a metric structure is a language such that for every predicate R, there's a predicate symbol, and an integer which aligns with its arity, closed bounded interval IP defined as the range of R, and a modulus of uniform continuity. For every function, there's a function symbol which represents it, and again has a modulus of uniform continuity. For every distinguished point, there's a constant symbol for it. And lastly, there's this non-negative real number, which is the diameter. Okay, the set of terms of our signature is built up in the standard manner from variable symbols, constant symbols, and functions attached to previous terms. If M is a structure given previously, the 0, 1 with bounded rational polynomials, and L is a signature over M, then things like this are terms, right? We have just the variable symbol by itself. We have the constant symbol 1/3 by itself. And then we have a bounded rational polynomial on it, right? X squared plus 1/2, bounded to 0, 1. The set of atomic formulas, which we denote by atom, contains expressions of the form P, T1 through Tn, where P is a predicate symbol of L and T1 through Tn are terms. Recall that D is also a binary predicate. Okay, so this is what our atomic formulas are going to look like. It's going to be something where we have the metric attached to it, or in a more general case where we have any predicate attached to it. But in our case, when we're looking at bounded rational polynomials on Euclidean metric on 0, 1, this is basically what it's going to look like. Okay, so we already sort of talked about this previously, but the set of well-formed formulas is defined as a small set of expressions such that any atomic formula is a well-formed formula. If U is continuous and phi1 through phi n are well-formed formulas, then U of phi1 through phi n is a well-formed formula. And if phi is a well-formed formula and x is a variable symbol, then we can attach sup or inf, and we still retain well-formed formulas. Okay, the length of phi, this is just the standard way that we define length. We count how many symbols appear in phi. Well-formed formula is quantifier free if no quantifiers, that is super inf appear in phi. And a well-formed formula is a sentence if all of its variable symbols are bound by quantifiers, that is, its truth value is fixed only by the structure. Set of all sentences of L is denoted by S of L. Define for any sentence the value of phi in M in the natural way. We're going to interpret all the symbols in metric structure and we're going to evaluate, right? So in our metric structure, Euclidean metric, right? If we interpret D from 1/2 to 1/4, right? These are all symbols representing them at the moment, but if we interpret them, then we just get the Euclidean metric attached to 1/2, 1/4, and we get 1/4, right? So that's its value in that structure. And for any sentence phi, we say that M satisfies phi, and we write M satisfies phi if the interpretation is equal to 0. Now, at times it might be useful to consider the satisfiability of an arbitrary formula rather than just sentences. Because of this, we can declare an assignment which assigns a unique point to every variable. Satisfaction is defined naturally. So we call T a theory if T is a set of sentences. We call a theory complete if there's an L structure, M, such that for every sentence phi, we have that phi is in T if and only if M satisfies phi. In other words, T is completely describing some structure. Now we define the degree of truth of phi with respect to T with this notation, phi to the circ, and we define this equal to the supremum of the interpretation of phi under all models which satisfy T. Now, if T is complete, we say that T is decidable if for every sentence phi, this value, phi circ, is a computable real, and moreover, uniformly computable from phi. Now, what the heck do we mean by computable from phi? We haven't talked about computability in the context of continuous logic at all yet, so let's talk about what we mean by that. So we're going to discuss effectivizing continuous logic. Recall that a name of a real number is a sequence of natural numbers which serve as codes of a sequence of rational numbers, such that those rational numbers converge to that real number and they are rapidly Cauchy. Now, a real number R is computable if there's some effective procedure which outputs a name for R. That is, R is computable if there's a CE name for R. That's the sort of classical computable analysis definition of a computable real. Now let's look at computable well-formed formulas of continuous logic. So to get to this, what we're going to have to do is define some new connectives. And they're not new, but there's, I guess, specified connectives. So we're going to take bounded subtraction, which is defined in the natural way. We bottom out at 0. We have negation, which is just 1 minus x. And we have the half operator, which just takes x and it divides it by 2. Note that all of these are continuous, and hence these are already connectives from which we can build well-formed formulas. Okay, so there's this theorem. This is corollary 1.6 in the Benyakov and Usviatsov 2010 paper. And it says that the set of functions, bounded subtraction, which I might refer to as dot div because that's my LaTeX name for it. So dot div, neg, and 1/2 generates for every n in the natural numbers a dense subset, L to the n, of the set of all continuous functions in the uniform convergence topology. All right, now when referring to woofs, we will normally drop the parentheses around neg.div and 1/2 as indicative of the symbols which represent them. And the set of L formulas of L, denoted L sub L, different L's, but you can see that. You can't hear it when I talk about it. But is the set of all well-formed formulas which include only neg, dative, and 1/2 instead of arbitrary continuous connectives, and L sentences and L theories relativized. Okay, so this is why we're doing this. While our old well-formed formulas had size continuum, we now have that these L formulas are countable, right? So this collapsed countability will be necessary for executing effective procedures on the set of formulas. Further, we can define an L topology on the well-formed formulas, and then given an arbitrary well-formed formula, we call a sequence of L neighborhoods which converge to that an L name of phi. So here's a corollary of the last theorem, and that's for every phi, for every well-formed formula of phi, there actually is an L name of phi. Okay, so if we're given a phi, by a name of phi, we mean a sequence of natural numbers which serve as codes of a sequence of L neighborhoods which form an L name of phi. And we say that phi is computable if there's some effective procedure that outputs a name for phi. That is, there's some C name for phi. And if T is the theory, we say that the map from phi to phi circ is computable from phi if there is an effective procedure which, given a name for phi, outputs a name for phi circ. Remember, this phi circ is a real number. So here we're taking a name of a well-formed formula and we are decoding it, and then we're trying to get a new name for the real number that's corresponding to this phi circ. Okay, let's talk briefly about computable presentations. Computable presentation of a metric structure M is a pair, and it's normally denoted with M plus or M sharp, Mg, such that G maps the natural numbers onto some quote-unquote dense subset of M in a computable fashion, and all the functions and predicates of M can be computed on the range of G. All the points of the range of G are called rational points of M plus, and computable notions relativize. Okay, so here's a classical result. This is attributed to Millar, and it appears in Harazanov's Pure Computable Model Theory survey. And it says, let L be a first-order language and let T be a decidable L theory. And there's a decidable model M such that M models T. This more or less translates to the continuous case. So what I'm trying to do right now is I'm trying to take results from classical computable model theory and I'm trying to translate them over to continuous first-order logic. Now this one was already sort of translated over. It was translated over by Wesley Calvert in 2011. He's the theorem that says if T is a complete decidable continuous first-order theory, then there's a probabilistically decidable continuous weak structure M such that M models T. But what I want to do is I want to consider the same problem in terms of computable presentations. At least for my advisor and me, we prefer to work with computable presentations, so we're reformulating this, and we want to know if it still translates. Okay, so what are we going to do? First, let's look at some arbitrary subset of well-formed formulas. We're going to let D be dyadic numbers. Now we say that this subset of well-formed formulas is Henkin complete if for every phi in the L formulas, every variable x and every pair pq in D such that p is less than q, there is some constant such that the supremum over x of phi minus q, or p minus phi when we replace x with c, is in gamma. Now, we can if we can extend T, or in this case gamma, to a maximally consistent and Henkin complete set, terms built up from these constants can form the rational points of a computable presentation of a metric structure M, which actually models T. So given a T, we're going to want to try and extend it to this maximally consistent Henkin complete set. This is the basic way of doing a completeness theorem. And so let's try and do that. So here's a lemma. It says any complete decidable theory T can be extended to a maximally consistent Henkin complete set lambda, where there's a uniformly computable sequence of lambda s's such that lambda is equal to the set theoretic lim-inf of those lambda s's. So here's a proof sketch of how to do this. We just throw in a bunch of constants at every stage so all the Henkin business works nicely. And then at each stage s, we're going to check all the well-formed formulas of length less than s for relative consistency up to an error term of 2 to the minus s. For each of those, we're going to put them into lambda s. Now, every single one of these is going to be effective. Actually, all of them are finite, but in the limit, they're going to converge to a maximally consistent Henkin complete set. Okay, so here's my version of the effective completeness theorem. So this is what I call the effective completeness of continuous first-order logic. It says let L be a signature and T be a complete decidable L theory. Then there is a computably presentable metric structure M such that M models T. So here's the proof sketch. We're going to extend T to the Henkin complete and maximally consistent set lambda as outlined previously. We're going to let M star be the model of T whose universe M star is the set of closed terms in C star, which is the Henkin constants. And we're going to interpret functions, predicates, and terms as themselves. Then M star by definition models T. Further, we can quotient out by the equivalence relation to get a metric structure. Now we're going to let G be any map which witnesses this computability, and we're going to define the presentation M plus as Mg. This presentation is computable since the rational points of M plus are precisely M star modded out by the equivalence relation, and we can compute the values of any predicate on terms up to arbitrary precision by checking a large enough lambda n from the previous proposition. And if you remember, those were uniformly computable. Okay, so that's the first result I wanted to present. Now we're going to move on to computational versus syntactic complexity within continuous first-order logic. So let's talk about the atomic diagram. We're going to define the atomic diagram, which we denote by D of M, to be the set of atomic L sentences or negated atomic L sentences which are satisfied by M. Now the atomic diagram of a computably presentable model is pi 0, 1. And this is pretty easy to show. We just have this relation. Theta S is going to be in the atomic diagram if and only if for all n in the natural numbers, M satisfies theta sub S minus 2 to the minus n. And this is a computable relation because M is computably presentable. Okay, so I list this as a classical quote-unquote result, but it's really a definition in the Harasanov pure computable model theory survey. It says that a classical model M is computable if its universe M is computable and some form of its atomic diagram is decidable. Does this translate to the continuous case? Not necessarily. Computably presentable structures can have non-computable atomic diagrams. And so here's a quick lemma for how we're going to prove that. There exists a uniformly computable sequence of real numbers C sub n such that C sub n is less than or equal to 1/2 if and only if n is in the complement of the halting set. So here's the theorem. There exists a computably presentable model M such that its atomic diagram is pi 0, 1 complete. So we're going to let M be this structure we were talking about before, 0, 1 Euclidean metric, bounded rational polynomials with the rationals. And now we're going to fix that C sub n that we were talking about previously, which codes the complement of the halting set. And now we can just check the atomic diagram because this function symbol f is going to appear in there, which is representing C sub n minus 1/2. And that's going to tell us exactly whether or not C sub n is less than or equal to 1/2. So from here, we're going to be able to decode the complement of the halting set. So this is pi 0, 1 complete. Okay, so let's look a little bit more into this. Letting L be a signature, we're going to define the sets sigma 0, 0, pi 0, 0, delta 0, 0, all equal as the set of all quantifier-free L formulas. Now for every n, we define the sigma 0 n formulas to be the set of all L formulas of the form inf of x of phi, such that x is a tuple of variable symbols and phi is in pi 0 n minus 1. And then similarly, we'll do the same thing with pi 0 n, except we're using sup instead of inf. So this is sort of the standard way of defining syntactic complexity, except in our case, of course, we have sup and inf instead of for all, and there exists. Okay, and then if I plug in sentences instead of just the language as a whole, these are going to relativize as the L sentences instead of the L formulas. Okay, so here's a theorem. This is joint work with Isaac Goldbring and Tim McNichol. It says, given a computably presentable L structure M with a computable presentation M sharp, then the set of all pairs phi r, such that phi is delta 0, 0, and r is dyadic. You can think of r as rational if you prefer. Such that the interpretation of phi is less than or equal to r is pi 0, 1. And if we have a strict less than, if we're looking for the interpretation to be strictly less than r, then that's sigma 0, 1. So we're actually jumping up in computational complexity. Okay, now in the pi 0 n case, checking the less than or equal to remains pi 0 n. But checking the strict less than jumps up to sigma 0 n plus 1. And in the sigma case, checking the less than or equal to jumps up to pi 0 n plus 1, but checking the strict less than remains sigma 0, 1. Right, so we're having this pattern where anytime we try and check a less than or equal to, we have this pi complexity, and if we're trying to check a strict less than, we have the sigma complexity. Moving forward, what I would like to do is I would like to generalize these optimal bound results that we had in the atomic diagram case to these further diagrams, these sigma and pi 0 n diagrams. Now these upper bounds were already proven as we showed. And then I'd also like to extend some complexity results to infinitary formulas. So this is where I'm looking to move my research forward with respect to my dissertation. All right, so here's my bibliography if you're curious about any of that. And please reach out to me at ccamry@iastate.edu if you have any questions, or you can comment on this video. I will do my best to keep checking this. I know some of my definitions were a little bit informal, so I can clarify those if you have any questions on those. and I can also clarify some things about the proofs or yeah, really any of that. But yeah, thank you so much for tuning into this video, and I hope you enjoyed it. Thanks.